Thank you, Chairman. Today, I will talk about the CSF fluid dynamics using the sediment or water in Macaca Fascicularis. It's a canicuizal in Japanese. Yes, I have nothing to disclose to this presentation. Yes, yeah, there are many previous talk about the CSF circulations and yes, yeah, more than 100 years, we also, 14 years, we teach us the CSF circulation is made by the choroid plexus and absorbed in the arachnoid granulations. And also, recently, we checked our textbook. Maybe nowadays, our students also teach these theories. But recently, it is said, maybe it is wrong. And they are new theory, but they are, yes, recently the CSF is segregated and reabsorbed throughout the all spinal fluid axis, and CSF circulates throughout the subclavian space and the pulse side to and fro, but exact understanding is not yet. They are very unclear region to the CSF circulation, also including the lymphatic system. And yeah, there are many methods to visualize some of the CSF circulation using the in vivo and using mainly in MRI. As one of the big method is the intracerebral injection of some contrast medium. And yes, today we talk about the intracerebral injection in the O70 water and gadolinium in the monkey model. Yes, in the previous report, yeah, there are some reports in rat model. Yeah, this shows that using the same to the O70 water and gadolinium DTPA, and for the O17, yeah, they are distribute intracerebral injection distribute the whole brain very rapidly, but for the gadolinium control medium, yeah, they gradually distribute in the brain. And yeah, but this is a video from their paper. Yes, it's the same. This time scale is 3.5 minutes. Yes, very rapid distributions water, but gadolinium is very gradually to whole brains. Yes, this is the time index curve of the brain and the CSF space and the frontal cortex in the normal. And yes, as shown previously, that to block it, aquaporin 4 channel using the TGN-N20 and yes, subclavian space is the same, but to insert is brain cortex, cerebellum, and the frontal cortex is reduced to the blockage of the aquaporin 4. Yes, that we tried to our monkey model. Yes, we tried on the 3 monkeys for the young one and the 2 aged monkeys, and we used 4.7 preclinical MRI. And first signal we intracerebral injection of the O70 water, and dynamic T2 weighted is obtained. And the next second is in the same, we injected the gadolinium control medium, and also carbon particle and dynamic T1 is also imaged, and 10, 30, and 1 and 4 hours, and next day. Yes, this is the image of the O70 water infusion. Yes, there are only the signal change here. And also you can see the signal develops in the cervical spines, and it's not go up, I think, upward to the brain. And this is a subtraction image. But it's not, the monkeys moves, it's not very beautiful, the subtraction image, but, and the CSF is a decrease, but I think the brain is not signal change. Yeah, this is the timing stage of the CSF space, and there are very clear drop and recovered in these three regions is here, here, here.
and the mediastinal magna and the cervical region, the signal is decreased and diminished. And B, another, the supra in the blue is here, fourth ventricle, slightly drops. And this is the preponderant system. They drops and maybe they keep their signal intensity. And for the upper side, it's true or not. And for the maybe lateral ventricle is gradually decrease. But I think this drop is too fast compared to the circulation of the CSF. This is a signal intensity of the brain parenchyma. I think there are no signal change in brain. We also try to inject the gadolinium, and in the change of the signal, and gradually, it's the same in the rat model. Gradually spread to the CSF space, and finally for the 4 hours, also brain parenchyma is enhanced, and wash out 24 hours. This is another case. Also same, to inject here and the fine drops of the signal intensity, and also, yes, this is a subduction image. Yes, this is time intensity curve of each CSF fluids, and maybe fine drops and recover to the mediastinal magna. And also, red is the cervical spines. And maybe this is but the other region is not to significantly signal change in this case, I think. This is the same in the brain parenchyma, and but I think in monkey model the brain parenchyma is not changed using the O7 water. And this is gadolinium injections, and but this is a little aged, and compared to previous case, the gadolinium circulation is a little delayed to compare to that. In the 4 hours, the previous cases enhanced the whole brain, but only the basically in the cerebellum and the more lower side of the brain. And this is a third case. This is a more aged, and you can see this case is only drop this region and subduction image, and this is some leakage of the extradural space. And this is a 6 inch of the CSF space, and in this case, the only drop is find on only the mediastinal magna, and the another region is not changed. And also brain parenchyma is the same. And this is a gadolinium injections, and this case the CSF maybe circulation is very limited using the gadolinium, and to wait the 4 hours, they only enhance the not brain parenchyma is enhanced in this case. Maybe summaries of the only 3 cases of the monkeys. Maybe introduction of the O70 water into the mediastinal magna lead to localized dispersion primarily within the adjacent system and the cervical subclavian space. The upper distribution of the O70 water towards the cerebral region is notably limited. Methodology did not reveal any signal change in the brain parenchyma signal post-injection of the O70 water. I think previous report and the difference of our method,
I think many changes are animal, rats and the monkey, and the O17 concentration is different 90% and 10%. I think it's better to need more high concentrations, and they use very slow infusions, and in our the manual injection, maybe very short time injection, and T2 and the IMR unit are a little different. This is a very answer. We only use the injection on the gadolinium. This shows that distribution of the gadolinium in the CSF circulation is more fast and more long. And 24 hours, most of the brain is enhanced, and the next 48 hours, they are clear. It's only 4 cases, but the intracerebral gadolinium distribution is different among monkeys, and maybe it's depend on some age or sub-age individuals. And yes, left 2 cases are a little similar, but the third case is not dispersed, only the, and last case is dispersed very wide range and detention. And in our research, we also inject the gadolinium and the carbon particles, and we also, after our experiment, we sacrifice the animals, and we check some distributions, the carbon and the gadolinium, and for the histopathologically. This is some case of the spinal canal, and we can find the carbon particle here, and we need to the histopathological examination with collaboration of the Oita University. Yes, some other in humans. This is on the Linsgaard in Norway. They do the many cases of the intercerebral injection in the humans, and they also the sequential change of the normal patient or some of the pathological patient. And in his report, this is reference patients. Maybe normal patient in 8 cases, and they also show in human, there are many different. It is 6 to 9 hours. The enhancement is very different for each individuals. In conclusion, the intracerebral control injection serves as a prevalent method for studying CSF circulation and lymphatic systems. In our experiment with monkeys, introducing O13 water into the megacentric magna results in its localized dispersion, primarily confined the cisternal adjacent to the injection site. As further research is needed to establish the O17 water imaging in tracing fluid movement in specific brain regions. And the circulation of CSF may vary between subjects. This variability suggests individual difference in the anatomy and physiology of the CSF and lymphatic system, highlighting the importance of considering subject-specific factor in these studies. Okay, thank you for your attention.